and to our second speaker and our last speaker of the afternoon session today will be Larry Cohen from the University of Sydney, and he'll be talking to us about quantum computing and error correction using LDPC code. Get away.
Great, thanks for the intro and thanks for inviting me to speak here. Yeah, so I want to talk about quantum computing with LDPC codes. So I think this talk will be a bit of a departure from most of the other talks during this workshop. It's going to be about error correction and fault tolerance. So I'm going to mainly talk about kind of two papers I've worked on, both to do with LDPC codes. So I'll just start by kind of introducing the general area and what these codes are all about. And then I'm going to talk about a method to do gates, Clifford gates, specifically fault tolerantly on LDPC code to kind of preserve all the important properties that we like about LDPC codes. And then I'll talk about another paper. Or I don't have the collaborators here, but I should say that this first paper here was in collaboration with Stephen Bartlett, Ben Brown, and Isaac Kim. And then the second paper, I want to talk about tailoring quantum LDPC codes for bias noise. And this was in collaboration with Yoshika Rossi, Darius Chandra, Amanda Quintavalle, and Al Campbell. All right, so I guess a bit of background. So, you know, everyone's trying to build a quantum computer. They're trying to create qubits. They want to do gates between their qubits. Obviously, qubits are not like transistors. They have massive errors that are, you know, big enough that if you just do your computation on the pure qubits, you're not going to get a successful outcome. So we need to kind of design fault-tolerant schemes for doing quantum computation. And pretty much I guess maybe the only real kind of fault-tolerant scheme is to make use of quantum error correcting codes. And one of the current disadvantages with the kind of popular quantum error correcting codes, like the surface codes, is the kind of the qubit overheads they require. So in particular, there's this famous bound due to Bravi and Terhal to do with local stabilizer code, really just local codes in general, which says that the number, so if you have n physical qubits and they encode k logical qubits with a distance of d, there's this bound that says that the number of qubits you can encode k times the distance squared has to scale linearly with the number of physical qubits. So in particular, you know, for like a local two-dimensional code, for example, this means that if you want, you know, like a constant rate code, so if you want to encode a number of logical qubits that scales with the number of physical qubits, then your distance is going to have to be constant. And conversely, it also implies this bound that the best kind of distance you can get in a local two-dimensional code is square root of n, where n is the number of physical qubits. And so for popular kind of fault-tolerant gate schemes on the surface code, like lattice surgery, this means that, you know, roughly, if you want to encode, you know, k logical qubits with a distance of d, you need something like 1.5 kd squared qubits, physical qubits to do that. And so a question people ask is, okay, well, you know, obviously this, you know, locality of the qubit operations is physically well motivated. Most of the architectures that we're trying to develop are more or less local, but suppose for a moment we forget about that locality. Can we improve on those bounds? Do those bounds still apply, relating our kind of encoding rate and our distance? And the answer is no. So just briefly, you know, obviously most architectures are local, but there are people trying to create these kind of non-local qubit architectures. So here I have, this was an experiment done by the trapped ion people at Oxford, where they're trying to kind of, you know, they're essentially like using kind of, I think, fiber optic cables and light to communicate between kind of far away trapped ion qubits, potentially even in different kind of modules. And then the second figure here is from a proposal, so not yet experimentally done, but a proposal from the Rydberg atom group at MIT, and they want to essentially put Rydberg atoms in this two-dimensional grid, and then like in each row and column, they're going to have a cavity, and they're going to use that cavity to shoot photons between the different Rydberg atoms, in a cavity, and it's going to allow them to do kind of these non-local interactions along the rows and columns. And then there are also some other architectures that people think would be particularly amenable to long-range interactions. So in particular, kind of photonic architectures, a lot of people hypothesize, might be quite useful for implementing these kind of non-local interactions. All right, so, what is a quantum LDPC code? It's pretty simple. So really, when we say quantum LDPC code, what we mean, strictly speaking, I suppose, is a family of codes. So we're going to be talking about a family of stabilizer codes, indexed by some certain number of physical qubits n. So that's this. And a useful method for kind of graphically expressing these codes is using what's called a tanagraph. So a tanagraph essentially splits up so you essentially write out for each check, so for each stabilizer generator in your code, you're going to write out this kind of check node. And for each physical qubit in your code, you're going to write out what's called like a variable node. And then you're going to draw an edge between the check node and a variable node if the generator corresponding to that check node acts non-trivially on the physical qubit corresponding to that variable node. And we'll say that we have this graph for a whole family of codes, and we say that this family is LDPC if the degree of the graph is bounded by some constant as n goes to infinity. And so LDPC codes originally come from classical coding theory, where people like them because they define these really good LDPC codes with great properties. In fact, in some regards, in the quantum case, they're actually even more important in a way, because in the quantum case, generally when we want to kind of measure a stabilizer generator, what we do is we kind of take another physical qubit to correspond to that stabilizer generator. We do like a bunch of C-naughts between that qubit and all the qubits in the stabilizer generator, and then we measure out that qubit. And so to achieve fault tolerance, we really want that syndrome circuit to be constant size, right? Because if that syndrome circuit, if the size of a stabilizer generator gets really big, that syndrome circuit gets really big, and it kind of builds up errors, and we're just going to end up with faulty stabilizer measurements. So that's really the kind of, from a fault tolerant perspective, that's one of the appeals of quantum LDPC codes. And then the other appeal, obviously, is the kind of better properties that you can get. Right, so here's some examples. So the first one is a surface code. It technically is a quantum LDPC code because the stabilizer generators have bounded weight as you increase the size. It's not usually what people talk about when they say quantum LDPC codes, but there you go. And then, here's a bunch of other ones. So maybe the first constant rate quantum LDPC code was the hypergraph product code. So that has a number of logical qubits that scale with the number of physical qubits, and it has a distance of root n. And the hypergraph product code it's more or less kind of like a generalization of the surface code. And then you have these other codes. And then, recently, at kind of the end of last year, there was finally someone managed to prove, so not someone, two, Pavel Pantelis and Kolechev proved the existence of good quantum LDPC codes. So these are codes where the encoding rate scales with the number of physical qubits, and the distance also scales with the number of physical qubits. But I think in this talk, we're going to be more focused kind of the hypergraph product code, and I'll maybe mention a bit at the end, the outlook for these kind of good ones. And just one thing to point out, so there's this result from last year that says that the better the properties the quantum LDPC codes have, the more non-local the interactions you'll need to be able to implement will be. So for, so here we can, for these kind of good quantum LDPC codes, they have better properties than say the hypergraph protocol, but they'll require even more non-local interactions. So that's just something to consider when when if anyone ever, yeah.
Can you tell us what you mean exactly by long range here?
Yeah, so here what they mean is if you were to put the qubits on if you were to put the qubits on like a two-dimensional grid, how far away is like the longest interaction you're going to need to do?
Right. Where is the difference between short range and long range?
Short range would mean like if you have a code family, as you kind of increase the size, the largest interaction you have to do will be, say, bounded by constant, not to be, or bounded by something that say like, I don't know, log in like the size of the grid. And like a long range thing would be like you always need to do like a n kind of length interaction. All right. So obviously just having quantum codes is not good enough. If you want to do actual quantum computing, you also need to be able to implement some methods for implementing fault-tolerant gates. So prior to this work, there's been a little bit done on this, but not that much. So there was a seminal work by Daniel Gottesman, where he used a kind of teleportation scheme along with he used like a kind of teleportation scheme to implement constant overhead computing with LDPC codes, kind of assuming given some assumptions. And then there was some kind of a generalization of lattice surgery for just specifically the hyperbolic codes. And then there was also a generalization of like grading on the surface code for the hypergraph protocol. But I think that all these schemes are mainly kind of focused on like asymptotic properties, and they didn't really offer a good way to kind of quantify what the practical overheads were for using these schemes. So that's something we were a bit more concerned about in this work.
Whenever you say teleportation scheme to do gates that make you think about magic state injection, is this different from magic state?
Yeah, this is a bit different. So this scheme is more like, this is kind of a pretty old school way of doing quantum error correction that people don't kind of think about as much anymore. But it's like, so it's kind of like magic state. It involves taking a whole code block, preparing a big resource state, and then you take another copy of your code block and you kind of teleport your initial copy through this resource state into this kind of third code block. And so depending on the resource state, that will do some kind of a gate. But in this Gottesman case, that's not just the magic state. You would need to do that for like any gate. You would need to prepare a resource state, which is like your whole extra copy of the code, your code block, and kind of teleport it through. It's a bit different to like magic state because you're not like injecting a magic state into your code. You're like teleporting an entire code block. And I guess we kind of just got to talk about this, so I don't need to go into too much detail, but so we will be kind of using kind of, assuming some kind of magic state distillation. And so given that, if you can do, logical Pauli measurements, then that gives you access to universal quantum computation. And so this is kind of like an example of kind of lattice surgery from the surface code, which our kind of scheme will be a generalization of. So here you have, like two kind of surface code patches, and each one supports a Z logical operator along the boundary here. And you do this merging operation, and this merging operation allows you to obtain the measurement result for this kind of ZZ logical operator. And that's kind of the basic idea. So let's kind of abstract that just a little bit. So you have this logical operator on your code. It's this parallel logical operator, and you want to measure it. And you can kind of think about measuring that as essentially adding this logical operator to your stabilizer group up to, the phase of your measurement outcome. But in general, for any decent enough, code that you're going to want to use, L is going to be not like a constant, not a constant weight operator. It's going to be something that grows in some sense with the number of physical qubits. And so if you just, you could just straight up do a measurement of the whole logical operator, but it's going to be kind of very high weight, and it's not going to maintain that LDPC property. And so what you want to do is you want to add this L. What you want to do is you want to kind of decompose L into a set of smaller operators, and then you want to add each of those operators into your stabilizer group. And this is kind of similar to a weight reduction scheme that Hastings also proposed last year. And so we add each of those smaller operators into our stabilizer group, and then when we measure each of those, and then when we take the product of those, they'll give us the measurement outcome for the logical operator that we want. And so in general, we're not going to be able to do this without having to use some kind of extra physical qubit. So there will be an overhead cost from this. And ideally, you want to keep this overhead cost not too large. We don't want it to kind of ruin the kind of constant rate properties of our code, at least not too badly. And we'll call this code, which contains these kind of extra new stabilizer generators and the logical operator, C merged. So let's kind of get into how to do that. So here I have, you can imagine this kind of rectangle, quadrilateral. It's like some representation, just some quantum LDPC code. And I should say that in this talk, we're going to be largely concerned with CSS codes. So those are the codes where all the stabilizer generators are only like power X to the power Z's. And that's just because pretty much all constructions of quantum LDPC codes are CSS. It's just easiest to work with. Right, and so this is some, there's some big quantum LDPC code here, and we're interested in a particular logical operator. So we're going to define this kind of graph induced by a logical operator. And so each of these kind of black nodes, so this is an X logical operator, and each of these black nodes is going to correspond to a physical qubit in that X logical operator. And then each of these red nodes is going to correspond to a Z generator that acts non-trivially on at least one of the physical qubits in that X logical operator. And in particular, one thing to note is that because all of the generators of your code need to commute, all the stabilizer generators of the code need to commute with all of the logical operators, each of these Z generators has to be connected to an even number of physical qubits in the X logical operator. And then we're going to define this other graph, which is essentially just the dual graph to this induced graph, right? So for each physical qubit in this X logical operator, we're going to define like a check node, which is going to be an X generator. And for each Z generator in this graph here, we're going to define a new physical qubit. And then we're going to create this ancillary system to measure our X logical operator. And it's just going to be alternating layers of the dual graph and this graph induced by the logical operator. And we're going to connect it up to our logical operator just like this. And then you can see if you take essentially, because each of these Z generators was connected to an even number of physical qubits, that means in this graph here, each of these physical qubits is connected to an even number of X generators. And so you can see that if you take the product of all the X generators in this kind of ancillary system, all of these, the action on all of these physical qubits is just going to go to the identity, and you're going to just end up with this X logical operator exactly when you take the product. And in particular, if you started with the quantum LDPC code where the weight of each node was bounded, then the weight of each node in this ancilla system is still going to be bounded. So you're still going to get an LDPC code when you do this procedure. And so that's how to measure like an X logical operator. Same applies for a Z logical operator, just with everything swapped around. And then another case we need to think about is suppose we have two X logical operators that are kind of disconnected from each other, so they don't share any physical qubits, and you want to do a measurement like XX. If you separately construct the ancilla systems for each logical operator, you're just going to end up doing a measurement of, of X on one and X on the other when you just want to do like a combined XX measurement. And so what you need to do is you need to kind of construct the ancilla system for each X logical operator. And then you just need to kind of like connect them up like this. And then you can see here again, if you take the product of all the X stabilizer generators in the ancilla system, you're just going to end up with, a measurement of XX, but not separate measurements of each X logical operator.
I apologize. Sincerely apologize. Still don't understand the graphical
So
of display. Is there a Tanner graph?
yeah, so this is a Tanner graph, right? So each
So each dot
is a physical qubit. Each black dot is a physical qubit, and then
red
each
and blue are the parity check.
are the stabilizer generators. So these are like the Z ones, and these are the X type ones. Yeah.
Okay. Great. Thank you.
Okay.
Now I need to process it. So far, everything nice and local, it seems.
Oh, okay. No, I mean, this is a graph. This is like a graph. So the things don't correspond to where qubits are actually physically placed or anything. So this will apply just as well if you're in some system where the qubits are applied in,
But
placed.
they could be laid out like this for now.
Yeah, but in a general like quantum LDPC code, they won't be. They'll be all over the place.
Oh, this is just kind of.
This is just
illustrate the principle.
Yeah.
The construction.
Yeah.
Mm.
I mean, this graph-based construction will always apply. It's just it's easiest to
It's
just
just kind
draw
of
it like this.
plain.
Yeah. But these qubits, like physically, I mean, obviously there'll be more than two of them in general, right? There'll be like whatever the distance of the code is, 20 or something, and could be if you lay them on a 2D grid, they could be anywhere. Maybe not anywhere, but they could be all over the place. Right, and then so we've kind of covered like how to do an X measurement and a Z measurement and like an XX kind of measurement. And then to kind of complete the whole thing, but kind of to do all the Pauli measurements, we need to do like a XZ star measurement or a Y measurement. And so it's a similar kind of principle. If you want to do like say an XZ measurement, so here we have some X logical operator and here we have some Z logical operator. And we construct the kind of ancilla systems for each one, but then to connect them up, we need to, do this kind of twist thing. But the basic principle still stands. If you take the product of these X stabilizer generators and you take these Z stabilizer generators and then these kind of white boxes here, which are also stabilizer generators, but not CSS ones anymore. And if you take the product of all of those, you'll get like an XZ kind of logical measurement. And I don't think I have a picture of it, but if you want to do like a Pauli Y measurement, it's kind of the same thing, but there'll be like an extra qubit down here, which will be acted on in a CSS code. If you want to do like a Pauli Y measurement, you take like the logical X, the logical Z, you get where they intersect will act like a Y there. And so you just kind of apply the Y down here. And so that's kind of the basic scheme, right? And that lets you do all of your logical Pauli measurements. And then when you add magic state, say to that lets you do universal computation. And so now the other important thing is that when we do this, the distance of the code is maintained. So you don't want the distance to become constant, for example, because then your scheme's not going to be fault tolerant anymore. So like here's just an example with just like the normal kind of surface code. Imagine you have like two kind of surface code patches, and you want to do a measurement of this kind of top boundary, which is you know, like some logical operator like x1 or x2, if you just kind of, you know, in this scheme, if you were to just kind of measure this logical operator using this, it would kind of be equivalent to like changing this rough boundary to a smooth boundary. But if you kind of just did that, you would end up with this kind of small logical operator that goes between, you know, these two smooth boundaries. And so that would kind of destroy the distance of your code. And so in this case, you need to kind of do multiple layers of these kind of these graphs when you construct your ancillary system. And if you know, it's easy enough to see if you do at least D layers, then definitely this logical operator will still have distance D. And then the other thing is, so in general, when we do this construction, it's going to like introduce extra degrees of freedom into our system. And so like here's an example. And the reason that is because essentially we're adding, you know, like in this example, you can see you're adding more physical qubits than stabilizer generators, and the number of logical degrees of freedom in a code is like the number of physical qubits minus the number of independent stabilizer generators. And so you're kind of adding in extra logical degrees of freedom here. And so like in this case, for example, what are the extra logical degrees of freedom? They are, so for X logical measurements, they are kind of the extra Z degrees of freedom are these kind of cycles here in the graph, and they kind of can be pushed up to any layer. And then the new X degrees of freedom are these kind of strings that go down the ancillary system. And we don't care about these degrees of freedom, right? We're not going to use them to do measurement. They're just kind of there. But the issue with it, and so because they're just there, but we don't care about them, we're going to treat this merged code as like a subsystem code. And these new degrees of freedom are going to be gauge logic operators. And so we need to check that those new gauge operators don't affect the distance of our code. And so that's something we prove in our paper, that essentially if you take one of the logical operators that you do care about that is storing information, and you dress it with these gauge logical operators, then that's going to still preserve, as long as again the size of this ancillary system is D layers, it's definitely going to preserve the distance to code. And it possibly you don't need to do all D layers for it to preserve it, depending on the particular code. But if it's at least D layers, then it will. And so let's kind of, what's the overhead of doing this? It's not like the greatest. So if you have some logical operator with weight L, and then essentially the size of this ancillary system in the worst case, for measuring a logical operator, it's going to be the weight of the logical operator, which is generally going to be like D, times the kind of distance that you want to preserve, right? That's how many layers you need. And so the size of the ancillary system is going to go something like D squared. And in particular, this means that if you want to like measure a lot of logical operators at once, the ancillary system can become quite large. It can become large enough that we kind of ruin the constant kind of overhead that we want. And so we need to kind of restrict the number of logical operators we measure at once. And so we define this concept, which we're not the first to define, called parallelism. And we essentially define the parallelism as the number of logical qubits that we act on non-trivially in each kind of round of parity measurements. So like in this example, we would have a parallelism of 6. So we could do like a 6-way parity measurement. We could do like 2 3-way parity measurements, so on. And we want to choose the parallelism to keep the overhead low. And so this is kind of a constraint in our system. It's not a new one. So in Gottesman's original work, he similarly needs to restrict the parallelism of his scheme in order to obtain constant overhead. Whether you can get constant overhead without having to restrict the number of kind of gates or parity measurements you can do at a time, I think is still an open question. Yeah, and so, you know, here we just have some numbers, not like, sorry, not yet, but actually, so certain codes you can kind of do a bit better than having, for example, a constant level of parallelism. So this is like a grid of the hypergraph product code. I'll just kind of roughly quickly go through it. Yes.
So, how does it logical measurements or on the TV?
No, sorry. So these are like logical measurements. We're not decoding from the codes. It's always encoded into error correction code the whole time. And this is just kind of, if you kind of create like a logical basis for your kind of code words, this is, you know, each one kind of represents like one of those kind of code words.
So it seems low parallelism is you stretch the computation in time.
Yeah, so
so in a way, I mean, there's a trade-off now between
yes, there's a trade-off
and operations. So but then maybe space is what you're most concerned with.
Yeah, so I think definitely in the near term, space is what you're most concerned with. Let me grab my charger, but I'll keep talking. One thing to point out though is, well, a lot of quantum LDPC codes, for example, are like single shot, which means that you can save a lot of time in the decoding compared to, for example, local architecture. So there might be some sense in which, while you have to incur an extra time overhead from this scheme, compared to like the local architecture, you save does anyone have a Mac? My thing doesn't like fit. My adapter doesn't fit into the. Oh, I see. This one's there. Yeah. Yeah. So while you kind of lose out on some time, while you kind of increase your time overhead from this scheme, you might be able to make it back up because if you're kind of decoding compared to like a surface code, say. But then one thing, so this is like an example of a hypergraph product code. And so this here, for example, is like a Z stabilizer generator. So all of these kind of squares, the gray squares, the light and dark gray squares are physical qubits. Each white square corresponds to a stabilizer generator. So this is like a Z1. This is an X stabilizer generator. And then here's like a Z logical, here's an X logical. And so for the hypergraph product code, on each row and column, you can actually support like root n number of logical operators. And so for the hypergraph product code, you can kind of construct like an ancillary system for just say like one column, and that will allow you to actually like measure out root n logical operators at a time. So that kind of allows you to improve your parallelism a bit past just the constant case. And so here's kind of some just basic numbers, kind of just not numerically obtained. That's something we still need to do, but just based on wanting to preserve the distance, right? And for a given level of parallelism, you know, how many extra, you know, ancillary physical qubits do you need? And so, for example, here we have like a hypergraph product code and a surface code with a given number of logical qubits and a given distance. And so if you restrict the parallelism, we get quite a big saving in the total number of physical qubits we need. If we have like a full level of parallelism, we still get a saving, like about half, but it's not as big for the same distance, but it's an improvement. And there is some question with regards to the parallelism about how capable our current algorithms are for actually making use of like being able to act on every physical qubit at the same time. Most algorithms, you know, only consist of like, you know, small gates, and you're probably only going to do a couple of them at a time. So that's kind of something to think about. And so now I kind of want to talk a bit about another work on LDPC codes to do with bias noise. So So often in error correction, we assume that our qubits undergo depolarizing noise. So this is an example of a depolarizing channel. We send in some density matrix, and we have like a we have a total probability of P of getting an error, and it's evenly split between like an X-type error, a Y-type error, and a Z-type error. But in a lot of, well, in at least some architectures that people are building, they're expecting that the actual error channel is going to be heavily biased towards one type of error. And so we define this kind of bias factor. So here's like a Z bias. And if this bias factor is much greater than 1, it means that, you know, there's a much greater chance of a Z error happening than an X or a Y error happening. And if that's the case, we want to kind of modify our code a bit to be able to take advantage of that biased error channel. And so this kind of is kind of the big work in the field from last year from the group at Sydney, not me, another group of people at Sydney. And they do like a very simple modification to the surface code, which was even mentioned, I think, in Paul's talk, which is, you know, if you just had a mod kind of every second physical qubit, you end up with a surface code that only has one type of stabilizer generator. It's this XZZX generator. And the important thing about this generator is that if you look at, for example, an X error, the syndrome will kind of look like this string here. So it will light up this generator and this generator. If you look at a Z generator, at a Z error, it will light up these kind of horizontal generators. And in particular, if you look at like the high bias regime, so if you're in like an infinite bias regime where you only get Z errors, your surface code essentially decouples into like a whole bunch of repetition codes. And repetition codes have much better thresholds and like error scaling than the surface code. And so in this regime where you have like a, obviously not infinite bias, but where you have very high bias, this gives like, you know, if you adjust your decoders, you need to add, if you're doing like minimum weight perfect matching, you'll need to add some weights to your kind of matching algorithm to account for the bias noise. And if you do that, you can get kind of big improvements in the performance of your code under bias noise. So we can look at this more in a more mathematical way. It turns out you can write the stabilizer. So this is a matrix, and each column in this matrix corresponds to a physical qubit. And each row corresponds to a stabilizer generator. And so like this is a matrix describing the stabilizer generator of just the standard surface code. And then doing this kind of Hadamard rotation involves essentially doing a Hadamard rotation to like the second set of physical qubits, which switches the stabilizer generator to this. So it's no longer a CSS code. And you can see here, for example, if you only have X errors, say, then you kind of don't care about the X generators. You only care about the Z generators. And you can see here how they kind of, if you only have X errors, this kind of just decouples into a, oh, I should say here that H1 and H2 are repetition codes. And so this kind of decouples into just a bunch of repetition codes. And so that's how you kind of get your good performance. And so you can apply this to LDPC codes as well. So we did this for this kind of these lifted product codes. It says 2021 here, but this paper actually went on the archive in like 2018, a while ago. And the basic idea behind these codes, if you take two matrices where each of the elements in these matrices is taken from some ring of like permutation kind of matrices, circular and permutation matrices. And then you kind of do a similar construction as before. You create this kind of big matrix, and then you replace each of the elements in that A with the kind of matrix representation, and that gives you this kind of quantum LDPC code. And the important part here is that, you know, just like the surface code, this code is kind of split into like two sectors. It's like one sector of physical qubits, that's these columns, and then a second sector of physical qubits, which is these columns. And so you can do the same kind of trick of kind of Hadamard rotating the second sector of qubits, which gives you kind of this stabilizer matrix. And then in the limit where, say, the X bias goes to infinity, you end up with just a bunch of decoupled codes which correspond to this A2 matrix. And so like in the numerical example we have an example where this A2 has a distance of 26 and this full kind of matrix has a distance of, we don't know exactly, but and so we have some numerical simulations and we run these using belief propagation plus ordered statistics decoding. And so belief propagation is a pretty popular algorithm for like decoding classical and quantum LDPC codes. And it's a message passing algorithm. So you send in a bunch of initial likelihoods of errors for each qubit. They pass messages on this kind of tanograph. At the end, you get the likelihood that an error, the final likelihood that an error occurred in each qubit, and you kind of use that to do a correction. The problem is that because of the kind of degeneracy present in quantum kind of stabilizer codes, often belief propagation by itself fails to find a valid syndrome correction. And so what you need to do is you need to take the likelihood output of belief propagation and you can chuck them into a post-processing algorithm like ordered statistics decoding, which will definitely give you a valid correction, a valid kind of syndrome correction. Not to say it will give you the right one, but it will be a valid correction. And so these are kind of numerical results. So this example is for I don't have it here, it's for a code with 416 physical qubits, 18 logical qubits, and some distance that we know is less than or equal to 20. And we can see that as we increase the bias, the X bias, the kind of total logical error rate decreases. And eventually it plateaus, which we expect because the kind of underlying code that it's kind of going towards as you increase the bias is also going to have, some particular error rate at some logical rate, error rate at a particular physical error rate. So it does kind of plateau, but we can kind of compare this performance to say just like a toric code, an XZZX toric code. And so we can see here's our kind of quantum LDPC code. Here's an XZZX toric code that encodes 2 logical qubits. And we can see that, like, I don't know why, right? This is maybe not the best example, but you can do an example where they have, say, more comparable distances, like a higher distance toric code, and you'll still see that the logical kind of error rate for the quantum LDPC code will be below the one for the XZZX toric code, up to some. So there'll be some certain very high bias where the toric code starts to beat out the LDPC code. And, depending on what you consider to be a physically realistic bias, maybe, here we can see at least up to 100, the quantum LDPC code still beats the toric code. And probably for a while still, it will beat it. And then at some point, it kind of won't anymore. But we can see that nevertheless, if you're using LDPC codes, just by doing this modification, you can get a big advantage under bias noise. And so that kind of brings me to the end. So let me just quickly say, in regards to the first part of the talk, one thing could be interesting to think about is how we can improve the overhead of magic state distillation using LDPC codes. And I think that's definitely, I think you can definitely do that. And then obviously one thing we want to do is reduce the size of the ancillary system, especially when we start talking about these good quantum LDPC codes with like linear distances. This scheme won't be good enough anymore. I don't know that there currently is a scheme for doing fault-tolerant computing at all with them to kind of preserve all the properties you want. So that's kind of something to think about. And then lastly, this applies to everything in this talk. And I think it's maybe the most pertinent issue currently in quantum LDPC codes, which is thinking about like more realistic error models, kind of full circuit level noise, and creating kind of scheduled syndrome measurements. Yeah, so thanks. That's it.
Maybe a small question. I saw that you had cardinal gates on code or something that.
Oh no, so sorry. So these H's, do you mean here? Sorry, no, these H's are not Hadamard's. They're like repetition. There's a parity check matrix for like a repetition code. So like a surface code, you can think of it just the product of two repetition codes. And that's all that this is kind of saying.
Do you think you want to turn your audio on?
It is on.
Oh.
Oh, you're saying to the.
Yeah, so maybe if I turn this off, then we'll get a bunch.
I literally can't turn up my volume.
Ross, if you want to go ahead and ask your question.
Thanks for this talk. When you're looking at these matrices here, and then you're saying that you applied some Hadamards to get you into the case for the bias noise, could it be that you could just pick maybe like a different symplectomorphism of this thing, and you could end up getting a better H for bias noise, or for different bias noise? Or am I getting kind of the wrong end of the stick of why these Hadamards made a difference?
Different way. So I think there's some work by Steve Lemire and some other people where they kind of, I think they kind of try to look at, essentially, they're not looking at LDPC code, they're just kind of staying with surface codes, but they kind of, I think, do a kind of numerical run of, okay, well, there are lots of, you can try not even just doing Hadamards, you can try doing lots of different things to, you know, different sets of the qubits, and kind of how good is it for bias noise. I can't remember exactly what the result was, but there's definitely a paper about, a recent paper from this year.
Okay, awesome.
Exactly that. So that, you know, if you're interested in that, that can be something. It's by Steve Lemire.
Okay, yeah.
And you have the word bias in the title.
Okay, thanks.
All right, are there any other questions?
Among these LDPC codes with a longer range interaction, do you have a favorite example that you research, and how bad is it with a long range? I mean, does it scale like n? I mean, do you have longest range distances or square root of n?
For like the good codes, longest range, yes.
Longest range.
Yeah, absolutely.
Okay.
Well, I mean, yeah, that's what the result in that paper shows. Do I have a favorite code? I don't. So the good quantum LDPC codes are new, and as far as I understand, there's no explicit examples of them, right? They're like, there exists. I mean, there's not a true kind of construction, and they're like, there exists. So
okay.
they're not explicit constructions.
I mean, it could be a dawn of a new era for quantum error correction. I mean, these surface codes, they've been around for a while, and maybe there is a competitor. I mean, are people thinking about how you transversal gates, or how to do gates with these codes?
So there are some recent papers about transversal gates. They don't manage to do the full Clifford. They just look at hypergraph protocols, and they don't manage to do the full Clifford group transversally. So you would still need to do something like these parity measurements to kind of at least get the full Clifford group. I'm doubtful that you can do the full Clifford group transversally on like these codes.
Is there some counterpart of kind of these topological methods, hole braiding or whatever, surgery?
So that's what this is, right? So mine here is kind of counterpart to like lattice surgery.
Mhm.
It works in the same basic way that you do all the parallel measurements. So you can do the full Clifford group, but with incurring some overhead. Obviously, like the thing about the nice thing about the transversal gate is you have no overhead, but so far they haven't been able to do the full Clifford group transversely. Grading, there's an earlier paper by Pauline and Krishna, that's this one. I don't think that it's ambiguous as to what gates they can do using that. They weren't able to actually say what gates they could do. Definitely no more than, obviously no more than the Clifford group with grading, but yeah, I don't think they weren't able to really say which gates they could actually do using that method. So currently there's like this Gottesman fault tolerant thing, and then there's mind B, which is like lets you do the full Clifford group. Yeah, and then there's a couple of things about transversal gates, but not the full Clifford group.
Are there any more questions from the audience? If not, let's thank both of our speakers again for that session.